Okay, welcome back to NLP. We're going to switch now to a very different topic, that of word sense disambiguation. So word sense disambiguation, as you can imagine from the name, is about automatically recognizing which of multiple meanings of ambiguous words is being used in a specific sentence. So words have different properties. We have seen this before. One of them is polysemy. Polysemy just means that many words have multiple senses. So here's an example. Let's have a drink in the bar. The word bar in this sentence means a drinking establishment. However, in general, the word bar has many other meanings. So for example, chocolate bar is another meaning of the word bar. I have to study for the bar, another meaning of bar. In this case, it means some exam for lawyers. And bring me a chocolate bar, and so on. Another property of words is homonymy. So for example, if I say, may I come in, and let's meet again in May, the word may appears in both sentences. It's pronounced the exact same way, and it means something completely different. Different books make different distinctions between polysemy and homonymy. So for the purposes of this class, we're going to focus on examples that are not homonymy by accident. So for example, the word may here is a verb, an auxiliary verb, and the word may in the second sentence is a month. So clearly those words are very different. They're different parts of speech and so on. So we're not going to be worrying about them so much. We're mostly going to worry about words, most typically nouns, that have multiple meanings. So we're not going to worry about words like round being a verb or an adjective or a noun. This is not part of what we'll do. So what are all the different senses of bar according to WordNet? Well, there's the first one here. Bar, or also bar room or saloon, is a room or establishment where alcoholic drinks are served over a counter. Another sense is a counter where you can obtain food or drink. So this is the actual physical piece of furniture on top of which you get the drink. Then bar is a rigid piece of metal or wood used for fastening or obstruction or a weapon, like bars in the jail. Next thing is a bar in music, and many, many other senses. I will probably spend another 10 minutes going through all of them in detail. So let me just show you the list. Here, as you can see, there's more than a dozen of those. So let's go back to word sense disambiguation. So as I said before, its main goal is to take a word like bar that has multiple senses that are numbered, let's say 1 to 15, and then in a given sentence to tell us which of those 15 meanings is being used. So obviously we have to do this in context. That's why we typically get access to the entire sentence and often to the entire paragraph or document in which the word appears. So word sense disambiguation is a very important component of natural language processing systems because it's used, for example, to come up with better semantic representations of sentences and also for question answering and for things like machine translation. Obviously, if a word is ambiguous in one language, that doesn't mean that it is necessarily ambiguous in another language. So for example, if you want to translate a sentence with the word play in English into Spanish, we need to understand what is the object being played. So for example, in English we say play the violin. In Spanish this is translated with the verb tocar el violín. And then in the sentence play tennis, we're going to use a different verb, jugar al tenis. So tocar and jugar are two different translations of play. And if we couldn't do proper word sense disambiguation in English, we wouldn't be able to translate those sentences into Spanish correctly. And then many other uses of word sense disambiguation. For example, for accent restoration. So the word cote in French means different things and it's pronounced differently depending on where the accents appear. So it could be something like côte, which is a coast, or côté, which is side, and so on. Another use is text-to-speech generation. So in this case, we may have a word that has multiple pronunciations depending on the meaning. So for example, lead or led in English. And then spelling correction. So we want to be able to distinguish between words like aid and aid with an E. And finally, capitalization restoration. So we have a word like turkey. If we know its meaning as a bird or as a country, we can properly capitalize it in some text that is not capitalized to start with. So let me now go over some of the common techniques used in word sense disambiguation, starting with a very old method by Michael Lesk, the so-called dictionary method. So the idea behind the dictionary method is that if you have ambiguous words in a sentence that appear together, you're going to find all of the possible meanings of each of those words, and then look up the dictionary definitions of all the senses of those words, and then look for pairs of dictionary definitions, one for each of the ambiguous words, that overlap the most. So here's how it works. We're going to match the sentence to a dictionary definition. Let's look at the sentence that has two ambiguous words. The first one of those is plant, which according to the Merriam-Webster dictionary has many senses. The first one of them is a living thing that grows in the ground, usually has leaves or flowers, and needs sun and water to survive. And then we have a second interpretation of plant, which we're going to call plant 2, which is defined as a building or factory where something is made. So that example is the word leaf. So the two definitions that we're going to consider are leaf 1, which is a lateral outgrowth from a plant stem that is typically a flattened, expanded, variably shaped greenish organ, constitutes a unit of the foliage and functions primarily in food manufacture by photosynthesis. And then leaf 2 is a part of a book or folded sheet containing a page on each side. So now suppose that we have a sentence like this. The leaf is the food-making factory of green plants. So we have the word leaf and the word plants, and we want to determine which of the senses of those are used in this sentence. So we have four possible combinations: leaf 1, plant 1, leaf 1, plant 2, and so on. So which one of those are we going to pick? Well, we're going to look for the overlap in the dictionary definitions and pick the one that has the largest one. Okay, so another method that was introduced in the early 90s by David Jarofsky, who was at UPenn at that time, is the decision list method. So here's how it works. It is based on the principle 1 sense per collocation. So in a previous lecture, we talked about collocations. So if I say living plant, the word plant is ambiguous, but the fact that it appears near the word living as part of a collocation means that we have the first sense of the word plant. And instead, if we have something like manufacturing plant, then clearly we have the second sense of plant. So the question is, can we come up with a list of such collocations that can give us hints to the disambiguation of the ambiguous words? Jarofsky's method is based on the idea that we're going to look at only two senses per word, and we're going to try to come up with a list, an ordered list of rules. Collocation gives sense. So if we have a collocation for that ambiguous word, we can automatically determine which sense we have. And the formula that is used for ordering those rules in the decision list is the following. We have log of the probability of a sense A given collocation I divided by the probability of sense B given collocation I. So since it's a decision list method, we have to sort those rules by this formula. And then whenever we have a new instance of an ambiguous noun, we're going to go through the list and pick the first item starting from the top that matches, and then label the word accordingly, and then stop. So here's an example of a decision list from the Jarofsky paper from 1994. He looks not only at collocations that consist of two words right in a specific order, he also looks at words within a certain window of many words. So for example, if we have to disambiguate the word BASS, which by the way can also have multiple pronunciations, for example, bass or bass, we're going to look at the following rules. If the word fish appears within the window, we're going to label this as bass, sense 1. If this doesn't hold, we're going to look at the next rule down the list. So if we have the collocation striped, followed by BASS, we're again going to label that occurrence as bass 1. The next rule in the list is guitar within window. So if we have the word BASS and the word guitar nearby, we now know that we have the second sense of that word as bass, or BASS2. And so on. So I'll have a few more examples here. Bass player indicates BASS sense number 2. And then play as a verb, followed by BASS. This is also BAS2, and so on. So we have rules that alternate between BASS1 and BASS2. So now let's look at a more detailed list of the type of features that are used in the Jarofsky decision list algorithm. I mentioned collocations. Those are the adjacent words on one side or the other of the word. For example, for the word bar, That could be chocolate bar, bar exam, bar stool, bar fight, or for words like aid, it could be foreign aid, which is one sense, versus presidential aid, which is another sense. We can also look at the position. It is important to realize that the collocation, like plant pesticide, is different from the collocation pesticide plant. The first one refers to the living thing sense of plant. The second one refers to the factory sense of plant. So position matters. We can also look at the adjacent parts of speech. So we want to know if the word that follows is a verb or an adjective and so on. We can also look at all the other nearby words, let's say within a window of plus or 5 words or in the entire sentence. And we can also look at syntactic information. For example, what is the subject of that word and what is the object of that word and so on. So for example, for the word play, we can look for the specific object, whether it's guitar or tennis, and then determine the sense from that information. And the overall topic of the text is very important. So one of the principles that Jarovsky introduced in one of the more recent papers was the so-called one sense per discourse principle, which said that most of the time, if an ambiguous word appears in a paragraph or a document, it's most likely to continue to keep the same sense within this entire discourse. So now let's step back for a moment and look at some general classification methods that can be used for word sense disambiguation. So word sense disambiguation in that sense is not different from many other classification problems in natural language processing, such as named entity classification or question type classification that we have discussed previously. So one of the most common techniques used is the k-nearest neighbor classification method, also known as the memory-based method. So the idea is this. You look at some current problem, for example, what is the sense of this word in this context, and then you look in your history of training data for similar examples and you figure out what decision you made at that time. And then that gives you the decision to make in the current time as well. So typically, people use a vector representation of each instance that needs to be classified, and then they measure the Euclidean distance between that instance and all of the other instances. So here's an example. We have a coordinate system here in 2 dimensions. Again, in the most general case, this is a much more dimensional vector. And then we have red objects here that form one cluster, for example, sense 1. We have blue clusters, blue points that form another cluster for sense 2. And now we are given with a new object here, and we want to determine how to classify it. So in a k-nearest neighbor algorithm, we're going to look at its nearest neighbor, one nearest neighbor. In this case, it's a red dot. Therefore, we're going to classify it as red. It is also possible to increase the value of k to some larger odd number, for example, 3 or 5. So in the case of k equals 3, we're going to look at the 3 closest examples in this vector space to the one that we want to classify. And then look at the majority class among them and return that as the correct answer. So in this example, we have among the 3 nearest neighbors, we have 2 red examples and 1 blue example. Therefore, we're going to label the hollow example as red as well. Okay, now let's move now to another method also introduced by David Jarovsky in the mid-90s called bootstrapping. So bootstrapping is an example of something called semi-supervised learning, and it has become one of the most influential algorithms, not only in word sense disambiguation, but also on many other NLP and machine learning problems. So here's how it works. We're going to start with one ambiguous word, for example, the word plant, 2 senses, let's say the living thing and the manufacturing sense. And we're going to come up with one very strong collocation that is indicative of each of those senses. So for example, for plant 1, we're going to pick the word leaf, and for plant 2, we're going to pick the word factory. So now we're going to build a classifier that looks at all the unlabeled data, and if it sees that the word plant appears near leaf, it will label it as sense 1, and if it sees factory, it will label it as sense 2. Now, since those are only single examples for each of the classes, we can only label a small percentage of the data. Let's say, for the sake of the example, that 1% is labeled as plant 1, 1% is labeled as plant 2, and the rest, 98%, is not labeled yet. Okay, so how does the bootstrapping process work? So now we're going to build a classifier that is going to look for other objects that were not classified previously, and it's going to look for additional collocations that appear in those labeled examples. So for example, if we have a sentence where the word plant appears near leaf, and near living, we use leaf already as a feature, but now we can learn that living is also a good feature that labels that particular sense. So somehow, in the process of bootstrapping, we're going to expand from the first seeds to some small number of labeled examples, then back to more features that are associated with each of those classes. And then again, by retraining a supervised classifier, we're going to get more labeled data, and so on. And this process is going to continue until pretty much all of the data points have been classified one way or the other. So bootstrapping, to summarize, is based on two important principles, both introduced by David Yarovsky. The principle of one sense per collocation. So again, given an ambiguous word, what word appears near it may help disambiguate the first one. And also one sense per discourse, meaning that all the instances of a word, of an ambiguous word in the same discourse unit are likely to have the same sense. So some of those methods that I mentioned before were trainable. So the question comes now, where do we get training data for word sense disambiguation? Well, there are several different places where we can go. One is to go to the SenseEval and SemCore data sets, which are available from public evaluation of sense disambiguation systems. This can be obtained from the senseeval.org website. And SenseEval is an annual competition that was done in two different events. The first event was the lexical sample task, where there was training data for a small set of words, things like bar and plant and board, each of which appearing in sentences that were annotated with the proper senses. And the second event, or the second task, was the so-called all words disambiguation task. That's where all the words in a given document had to be disambiguated. Now, in each of those cases, the senses in this manual annotation were obtained from WordNet. So SenseEval data, and more recently SemEval data, is available in many different languages in addition to English, so languages like Spanish and Romanian and Dutch and so on. Another way to train data for word sense disambiguation is to use the so-called pseudo-words principle. The pseudo-words principle says that we can take a word that is not ambiguous and another word that is not ambiguous and combine them into a new word that has all the instances of both of the unambiguous words. So for example, every time we see the word banana, we're going to replace it with a single token that stands for banana or door. And we're going to do the same thing for every occurrence of the word door in the document. So we have those tokens that could be either one or the other. And then we can train this, we can train a classifier, because we know in each instance what was the actual word that was used. So the word sense disambiguation system is going to see this collapsed word, and it will try to guess the correct word. And there are also multilingual corpora that are aligned at the sentence level. So for example, if the word play in English is aligned to jugar or tocar in Spanish, we can use that information as training data for word sense disambiguation. So some brief results from one of the earlier SenseEval evaluations. The metric that is used in word sense disambiguation is based on the following quantities. A is the number of assigned senses. C is the number of words that are assigned correct senses. T is the total number of test words in the evaluation. And then precision is C divided by A, and recall is C divided by T. So just our basic precision and recall evaluation metrics. And to give an idea of the results, the best performance in SenseEval 1 was around 77% precision and 77% recall, whereas the best that human lexicographers could get was in the high 90%. And one interesting heuristic is that if you have an ordered list of senses for each word, with the most common sense appearing first, you get some decent performance, 57% precision, 50% recall, which is still not close at all to the best automatic systems, but still gives you a decent baseline. One caveat here, however, is that this method works better if the text is relatively homogeneous in terms of genre and domain. Once you have texts that are for multiple genres or domains, this method is unlikely to work because the most common sense of that word changes according to the domain. So this concludes the section on word sense disambiguation.